A large stone block is used on a building site to put pressure on the ground beneath the block, making it more compact. The diagram below shows the appropriate block. All right, using data from the diagram below, calculate the pressure on the ground from the block. All right, so for this, we're going to use the equation pressure equals force divided by area. That's just definition of pressure. So the force, they tell us here, is 9 times 10 newtons, so 9 kilonewtons, all over the area. And the area is just going to be the area of the block. We don't care about the height. The height is basically, you think, oh, a bigger block would cause more pressure. That's true, but that's because a bigger block would give more force, more weight going down. So for this case, pressure, what we're concerned with is the area, which is length times width, which is going to be 1 meter times 0.6 meters, which is going to give us 9 times 10 to the third all over 0.6. And this is meters and meters. So this becomes square meters, newtons per square meters, which is pascals. I could do this in a calculator, but I'm going to try to do it in my head. This is 6 times 10 to the negative 1 newtons per square meter. 10 to the negative 1 on the bottom is the same as 10 to the first on top. You basically just switch that little negative. 9 over 6 is 1.5. So do 1.5 times 10 to the fourth pascals. And pascals is a unit of pressure, which is newtons per square meter. All right, so now we want to find the mass of the block. So for this, we're going to do weight equals mass times gravity. Mass is what we're trying to find. Gravity is 9.8, and weight is 9 times 10 to the third newtons. So the mass is going to be weight divided by gravity. That's supposed to be a g, which is 9 times 10 to the third all over 9.8. I'm not going to do this in my head, so let's go to the Wolfram. Over 9,000 divided by 9.8. It's actually not over 9,000. It's exactly 9,000. So 9.18. Yeah, I'm good with that. Boom. 9. Did I say 908? 918? 918. Yep. 918 kilograms, which is a pretty stout block. Find the density of the block. All right. So the mnemonic I use for this is density is love. So what you do is you draw a heart, draw a line through it. The top of the heart is kind of like an M. Bottom of the heart is kind of like a V. So density equals love. The mass we know is 918, and the volume is 1 meter times 0.6 times, I think it's 0.6 as well. 0.6 meters by 0.6. Yep, 0.6. This gives us 918 divided by 0.36, which is going to be like 3,000. Is it? I don't know. Let's figure this out. So this is 918 divided by 0.36. I was way off. 2551. And that gives us 2551 kilograms per cubic meter, because that is the units of density. All right, so now we got that. The builders of these two large blocks. The builders have 2 of these large blocks. Okay, sounds reasonable. Explain the pressure change in the ground, if any, by putting the blocks one on top of each other. So if they're one on top of each other, the pressure will double because the weight is going to double. You have, so pressure equals force divided by area. Weight is a force, and so the force due to gravity pushing down is going to double, so that's going to go up, but the area along the ground stays the same, therefore pressure goes up. Side by side, the pressure is going to stay the same because even though, so pressure equals force divided by area, even though the force went up because you have 2 blocks now, the area that's in contact with the ground also went up. And it did it in such a way that the pressure is just going to stay constant. So side by side, same and double. A gas tap in a school science laboratory is tested. The force produced by the gas coming out of the tap is measured to be 0.1 newtons. The opening of the gas tap has an area of 0.5 square centimeters. Calculate the pressure of the science laboratory gas supply. All right, so for this, we're going to say pressure equals force divided by area. We want it in SI units. So it's going to be newtons, which is, we know is 0.1. And newtons is SI, so we're good with that. Then we have 0.5 centimeters squared, which we need to convert over to metric, i.e. meters squared. And so what we're going to do is I'm going to start by rewriting the centimeter squared, not as centimeters squared, but as centimeters times centimeters. So squared just means you multiply it by each other twice. So centimeters times centimeters is the same as centimeters squared. That's convenient because that helps us visualize the conversion better, because then we have 100 centimeters per 1 meter times 100 centimeters per 1 meter, and we can see that each of the centimeters cancel out, and we're left with 0.1 times, and I'm going to call this 10 to the 4th, because each of these is 10 to the 2nd, 10 to the 4th, all over, and this is going to be newtons, all over 0.5 square meters. I'm going to rewrite this one more time as 1 times 10 to the negative 2nd times 10 to the 4th, all over 5 times 10 to the negative 1st. Did I say second? I meant, so 10 to the negative 1st. Time to the negative 1st. This would be newtons, square meters. And then basically I'm converting this 0.5 into 5 times 10 to the negative 1. That way I can kind of combine the powers of 10. But here they can conveniently cancel. And so we have 1 over 5, which is 0.2 times 10 to the 4th, which is 2 times 10 to the negative 1 times 10 to the 4th, which is 2 times 10 to the 3rd pascals. Which sounds like a lot of pressure, but really a pascal is not that much. So this is the gas pressure, 2 times 10 to the 3rd pascals. So calculate the pressure, check over there, 2 times 10 to the 3rd pascals. The liquid-filled U-tube is connected to the science laboratory as shown in figure A. Pressure from the gas pushes the water higher in the right arm of the tube than the left. The device is then used to measure the pressure of the gas in a school technology room. Okay, state the name of the U-shaped device used to measure. This is referred to as a manometer or manometer. Manometer. I'm pretty sure it's manometer. Using the data from A, calculate the pressure in the technology room gas supply. We said that the definition of pressure is force divided by area. Well, another way of writing that is rho GH, where rho is the density of the fluid, G is gravity, and H is the height of the fluid. So for this, you could derive this formula by breaking things down. And basically this is mass divided by volume times gravity times height. Move this volume over here. H divided by volume is kind of like area. And so then you get mg over area. That's the force due to gravity. And you get back to this force divided by area type thing. So this is the formula we're going to use. So using the data from A and B, calculate the pressure. And so looking at this, using the data from A and B, calculate the pressure in the technology room gas supply. So we're given the one in the science. Okay, so pressure science room is going to be rho GH. So this H here is from the top. So if we look at this over here, the way to view this is you break it into two like this. And this fluid over here is exerting a force this way. This fluid over here is exerting a force that way. And since they're symmetrical, they're going to cancel each other out. So we don't care about those. We look up here. This is gas. And this is probably air. So probably just, nitrogen and oxygen. A little bit of argon. Their densities are going to be small. So we're going to say that they're negligible. And we're also going to say that this is negligible as well. So all we're left with is this pressure over here from the gas and this at pressure atmosphere. We're just going to do this in terms of gauge, meaning that we're going to assume that pressure atmosphere is 0. It's not that the atmospheric pressure is 0. It's just that we're talking about the pressure of the gas supply in relationship to how much higher it is than atmosphere. So, long story short, all we care about is this 10 plus 10 centimeters, i.e. 20 centimeters of fluid right there. So the pressure in the science laboratory is rho GH. Now they don't tell us, they do tell us water. We're going to go with this. So the density then is going to be, let's see, they told us the School of Science lab. Yeah, let's see what happens. So we know the pressure because we just found it 2 times 10 to the third. We know gravity, which I'm going to just say is 10. I know it's 9.8, but 10 is just convenient here. And then the delta H is 2 times 10 to the negative 1. So it's 0.2 meters, which I just wrote like that because, again, convenience. And so when these cancel out, 10, 10, 1, we get the density of this fluid is 1,000 kilograms per cubic meter, which is about the density of water. So that makes sense. So we actually don't even need this. If they didn't actually have to tell us what this fluid was. They did tell us it was water, so we could have just guessed immediately 1,000 kilograms per cubic meter. But I wanted to do that just to check. So now I want to know the gas pressure in the technology room. And since this is 50% bigger, I'm assuming this is going to be 3 times 10 to the third, or 50% bigger there. But we can calculate it. Pressure. Now I want to use a different color here. I know, getting a little bit messy. And for that, I apologize. Pressure technology, that's a terrible P. Yeah, I'll fix the P real quick. Pressure technology equals rho GH, where this is the density of the fluid. We know that's 1,000, which is 10 to the third. Gravity, which I'm calling 10 for convenience, times the height, which is 3 times 10 to the negative 1. We have 10 to the negative 1 and 10 to the first cancel, and that gives us 3 times 10 to the third pascals, which intuitively makes sense. The gap in the manometer was 50% bigger, 10 versus 15, and so the pressure was also 50% bigger. So using the data from there to calculate the pressure in the technology room, this is 3 times 10 to the third pascals. And that all goes back to pressure equals rho GH. So I hope that helped. See you next time.